Right, so I'm going to talk about understanding outlier populations in astronomical time series. This is not a particularly new subject. This is a historic outlier. If you looked up in the night sky about 2100 years ago, you would have seen a strange object which was moving somewhere between the Pleiades and Taurus, and nearby to Jupiter, and this would be different from what you would have seen the previous night. We heard about the Hipparchus catalogue this morning, so 1,000 objects that you probably would have seen in the naked eye then. This would have been different, and you would have made some interpretation of it according to the particular model that you were thinking about. And this particular outlier repeats through most of our recorded history. It's a significant outlier. Gets various things attributed to it, that's when you should change a king in England, this is when you should have the fall of Constantinople, this obviously is wrong, because this is not the birth of Christ, but at least it affects the medieval art. And we know it today to be Halley's Comet. So, astronomy, especially time domain astronomy, things have changed. There's been a very good source of outliers for much of recorded history. And with the change of, or the re-emergence of time domain astronomy through these nice new large telescopes, nice new large detectors, nice new computing facilities which enable us to make these cinematographic images of the sky, we are really in a renaissance of time domain outliers. Things like Palomar Quest and Catalina striving too slow, and now moving into these areas of the Palomar City Transient Factory. Pan-stars, as we heard, will have their data released sometime in the next couple of weeks, we hope, finally. Sky Mapper, and we've got ASCAT and Thundercat, and Meerkat, the Pathfinders for SKA, Gaia, LIGO. If you believe the rumors that are going around, LIGO may have already detected something. Maybe not, we don't know. They'll let us know about 3 months' time. Maybe just be another event that they've inserted. IceCube detecting things in neutrino. So we're really detecting all sorts of interesting things in the time domain now, right across the EM spectrum, even outside of the EM spectrum, and these get associated with things from the scale of solar system objects up to extragalactic things at the very large scales and very far back in time. So, sort of trying to understand this population of astronomical outliers is really quite important. Now, the survey I work with most closely at the moment is the Catalina Real-Time Transient Survey, which you've heard some stuff of from George. This is a collaborative survey with the Catalina Sky Survey, which runs out of the Lunar and Planetary Lab at the University of Arizona. Catalina Sky Survey is a Earth asteroid. We're looking for the killer asteroids. The basic deal we have with them is we piggyback on top of their data stream. Anything within the solar system is their purview. Anything outside of the solar system is our purview. Unfiltered observations, pretty nice per illumination, covering 2,000 square degrees of light, covers 33,000 square degrees because we have telescopes in the south as well as the north, up until about 2 years ago. Calibrated photometry, 500 million objects, more than 1 billion data points, non-linked about 20th magnitude. This gives us roughly about 250 observations for each of those 500 million objects with a 10-year baseline. So if you think about the LSST figures you've heard, that's LSST gives you 200 observations in a single filter over 10 years. With Catalina, you get about 250 observations over a 10-year baseline. So in terms of sampling, in terms of cadence, it's very similar. The same sort of scope of data that you might want to work with timescales. We have an open policy on the data, so all the transient alerts are made public immediately, and the data archive is online, and you can pull up the light curve for your favorite object if it's in one of those 500 million. So in terms of scale and such, George has already alluded to this, that we're currently about a 3% LSST. That's 2 to the minus 5, so if you assume 5 iterations, that will take you there with more sort of time of about 18 months. So it's the right sort of scale now to what LSST will be in sort of 10 years' time. So it's a very good data set to work with to get some idea of sorts of problems and challenges that you will be faced with when you want to work with an LSST scale data set, and you want to take technology considerations into account. There is a successor which is going on underway now that we're funded to have the same telescope with bigger cameras, which will increase the field of view and increase the amount of area we can cover at night, and playing around with the cadence of it as well to increase the transient rate and maybe look for more interesting stuff on a different temporal cadence than we've currently been doing. And that's getting underway now. First checker is just being put onto the CSS first, isn't it? Or MLS first. So that's happening now, so that the data will be increasing. So it's a great data set to work with, but obviously we have 500 million time series, 500 million light curves, and what we need to do is to try and actually understand it in some easy way. It's not a case of looking at everything. Unfortunately, this is real data, it's not simulated data, so it's noisy, it's gappy, it's heteroscedastic errors, it's terrible as far as computer scientists are concerned. You may have 20 data points for one object, you may have 600 data points for another object. So obviously if you want to do comparisons on a statistical basis between these, you need to transform the representation of these into something that's more homogeneous. And this is where we talk about features. So what you want to be able to do is to distinguish that object from something which is maybe not so interesting. And of course what we do is we start thinking about how can I do this, and we define things, obvious things like maybe what's the amplitude of the variation, or what's the slope, are there any trends that we can see that some objects may have changes over a long time and others are fairly constant, or maybe we go for something more sophisticated and you try and decompose the time series in terms of a set of basis functions, and then you use the coefficients of the decomposition as an alternative representation, very similar to the sort of dictionary techniques that John Luke was talking about. And you can build up all sorts of different features to try and understand this and see how they relate. So what we've been doing for the last couple of years is we defined a test set of about 1.5 million light curves, which is composed of 1 million variable objects, and then a control sample of 500,000, which are not variable according to certain criteria, and being sort of measuring various features for all of these to see what we can carry out and figure out. Now there's been some reference to the Richard et al. Feature set, which is used quite a lot in the literature. But one of the things we've discovered, and it's published in other work as well, is that it's a great first step. But unfortunately, a lot of the features that are in that data set, in that feature set, do not actually carry out much discriminatory information when we're trying to distinguish between different classes of object or different types of behavior. And that's because they're fairly obvious features. They're things like flux ratios and whatever. And what it would be much better to do is that, we understand, or we believe we have a fairly good idea or grasp of the types of physics that we see or expect to see in astronomical sources. We know, there's hot gas involved, there are magnetic fields involved, there are rotations, pulsations, eruptions, all that sort of thing. And wouldn't it be better if we could actually define a set of features which are can capture the types of phenomenology we expect to see in terms of the time domain, instead of something which is just sort of statistically motivated. So we've been through the literature, not only astronomical literature, but other types of time series analysis, people who look at biological systems, people who look at chemical systems, people who look at financial systems, to see what types of statistics that they use to capture different types of phenomenology that they're interested in in trying to understand and try to capture. And so we have a set of about 100 features that we have measured for these 1.5 million light curves, capturing, well, maybe trying to encode something about morphology or scale or different variability measures, characteristic time scales, memory processes, can we capture measure nonlinearity or chaotic, or then different types of dictionary representations, hidden market models, continuous or regressive, that sort of thing. So a much more broad set. Our aim is that for a single light curve, we probably could measure those 100 features in less than 90 seconds. Obviously, there was a mention yesterday about what you really want to be able to do is capture that all in 1 second, but let's figure out which are the useful features first, and then you have a much smaller feature set, and then you can get the clever coders to implement that on a GPU or to do it. This obviously defines a very high-dimensional feature space, though, what we want to do is trying to understand what the different types of areas or objects that inhabit this feature space. There's this. We can break down the sorts of processes that contribute to variability into those which have some sort of deterministic process behind those, and those that are the result of some sort of stochastic process where there's essentially a random element involved. And this is a thing called the Decomposition Theorem, which basically says that for any stationary process, anything that's got a well-defined covariance matrix, you can regard it as the sum of a moving average, which is giving you your stochastic terms, and a linear deterministic process. And that means that any time series out there may have a more dominant deterministic component or a more dominant stochastic component. And that will give you some idea of possibly what the physics underlying the variability that you see. It begins to give you some insight that what we're seeing here is deterministic in origin or stochastic in origin if we don't understand what the origin is. So one of the things we're interested in doing is trying to see whether we can actually separate those out. So those occupy different areas of the feature space in terms of the sort of things that how they manifest in those phenomenological features that we're interested in. We have our 1.5 million light curves, we have our features for this, we can construct a very high-dimensional feature space, and these characterize distributions then in terms of the different types of phenomenology that we're looking at, or the different types of features the different distributions of the different features, and with each axis being one of those features, will tell us about general population behaviors. That we have a million variable objects, we would expect, this is what the variability spectrum is. We believe we're fairly representative in the sorts of things that are susceptible to be. There may be some 1 in a million objects in there, but the broad class of astronomical objects, because we've got quite a good data set, we believe, is going to have that sort of distribution, and that will tell us about the general population and how that's behaving. Now you can sort of think about this from a topological aspect, and that you believe that the global shape of the data in the semi-dimensional parameter space can provide information about the phenomena that they represent. That because they are characterized in terms of these phenomenological behaviors, and because there may be a difference between what a deterministic process and stochastic process is contributing to the overall time series, that the actual shape of the parameter space will allow you to say something about that. This is particularly in the case where one of the problems of trying to do a low-level representation or a low-level visualization of these very high parameter spaces is this is particularly these sort of planar projections that we do to try and understand just sort of two variable correlations or whatever, may not be particularly representative when the space is too high dimensional, or possibly the actual relationships are multivariate, or there's a very twisted representation. And so is there a different way that we can analyze these distributions in this very high dimensional space, which allows us to infer information about what may be going on? And this is the sort of topological aspect, the topological analysis of these high spaces. And so what we're interested in some ways, we're actually interested in the properties of the space itself that the data create. So you have your point cloud data, and you can ask generic topological questions about what is the shape of this in this high dimension, and can we relate that to meaningful things. So this is a thing called topological data analysis. The way it breaks down is that what you're interested in doing is you're interested in trying to identify the features, the topological features, the number of components or different components which may be contributing to your overall data set, the holes, the graph structure, notions of connectivity, which persist over a wide range of length scales. And this is a thing called persistent homology. And the idea is that those features which actually persist over a wide range of length scales are more likely to represent true features of the underlying space.
What do you mean by length here? Physical length or?
Yeah, I'll come on to that in a minute. Rather than being artifacts of sampling noise or parameter space. So here's an example. I have 4 data points in my parameter space. And around each data point, I start growing a circle of increasing radius. So at one point, they will all suddenly connect up, and they will create a hole. Okay? So that's called the birth of the hole. The hole here is a topological feature telling me something about the distribution of my points, about the feature of the distribution in my space. I will keep increasing that length until at some point the hole gets closed up at a separation B2. And then that's called the death of this feature. Now at some point, if I keep increasing this, all the points in my point data cloud will form a single entity, and that's the end of the analysis. Now, the idea is that I can use the length from D1 to D2 of this ever-growing thing that I'm using to analyze the properties of my space as a measure of how persistent it is. So, the idea is that things which are noise or sampling or whatever will be very short-lived features. Things that are actually true properties, true topological properties of the underlying space will be persistent, will be long-lived. And this sort of analysis is believed to be invariant for data perturbation, and so that's going to tell us something actually fundamental about the nature of the space, and then I can use that as a discriminatory thing to try and understand what's going on underneath. Now this is, I don't only need to do it in this dimension, I can increase it to a number of higher dimensions, and what you end up with is, because this is topology, you will end up with a whole slew of these persistence length for the different features at the different dimensions that you see in the thing. And in terms of persistent homology, this is called the barcode of the parameter space that I'm looking at, and then you can do the analysis of the things in terms of other features and use that as a discriminatory one. But the idea is that there is topological information that I can glean in terms of those things that are persistent, or through some sort of persistence analysis over different range scales in my data space that would allow me to say something about the topology and therefore something about fundamental processes maybe going underneath, because that's what topological data analysis sort of infers. Now, it can be quite convoluted to do this. Is there an easier way or a short way that I could do this computationally, which allows me to get the same information out in a slightly more constructed form. So how, given my point data set, instead of trying to do a Dubrovnik triangulation and then building up these simplicial complexes, as they're called, to try and do this, is there another type of operation that I can do that allows me to do something which is, you can show is algebraically related and gives me some of the same sort of information that I'm interested in. Now, from graph theory, there's a thing called a minimal spanning tree, which is basically a glorified way of doing join the dots. It's very similar to the friends of friends algorithm that Sarah was talking about this morning. It's very similar to percolation analysis. You can show it's very powerful. Now, the minimal spanning tree for a data set is a unique construct. You only need to construct it once for the data set. It can be shown mathematically to encode all the relevant information about connected components at all resolutions. It's invariant under rotation, scalings, and translations, so it's ideal for topological analysis. Those are the sort of things that are topologically so here we have a data set. This is the minimal spanning tree for the data set. You see that you have leaf nodes which are only connected to one. You have some nodes in the middle which have more things connecting them together. There are no circles in it, no cycles rather. There have been various large-scale structure analyses that are being done in astronomy to identify structures doing this. There's a nice example of doing the Sloan Great Wall in Jellicoe's book, so you can go and look at that. Now what you can do is, when you've done this for your data set, there are various ways you can break up a minimal spanning tree to identify clusters or subtrees. You can remove edge lengths between, you can say I'm going to remove all edge lengths which are greater than some particular length scale, and then that will divide my full structure up into a number of subtrees or subclasses. And what you can show is that this pruning of the tree, as it's called, is equivalent to a compact partitioning of the space that you're interested in, and that the clusters that it produces are precisely persistent components. So what that means is that they are equivalent to these sorts of they're equivalent to the sorts of structures in terms of persistence that I would see if I was doing the topological analysis. And because that's the case, I can also derive algebraic topological measures from those which are equivalent mathematically to others that I would derive from if I was doing a variant topological analysis. The asymptotic behaviors of minimal spanning trees are also well understood, so there's a nice amount of theory from mathematical theory behind them that places this on a good footing. So where's this all going? The idea here is, so how can I identify outliers in terms of a topological approach in my very high dimensional parameter space? Now there's this great definition of what an outlier is. Now from a topological perspective, an outlier, significant outliers, are going to have high persistence in the sense that they are going to be things that hang around for a long time on the edge of your distribution before they get subsumed into your final amorphous cloud of everything, because they have something which separates them out from the rest of the thing. And they also have marginal connectivity. So this is different from a density-based approach. In a density-based approach, you would expect outliers to just live in a low-density region. In a topological approach, the high persistence is somewhat equivalent to the low density, but you also expect it to have marginal connectivity in the sense that it's going to be a leaf node, or it's going to have what's called the degree of the node, the number of things it connects to, is not going to be very high, because an outlier is not going to be connected to the more regular clusters, which are illustrative of different populations within your data set anyway. It's non-parametric. There's a complementary approach you can do also to identify what are called hub nodes, which are in some ways they're a type of outlier as well, but they're the things that will actually connect up different classes or different subclasses in your data set. So this is coming from a graph-based approach as opposed to a density-based approach, but they're the ones which may allow you to connect up two different subclasses in your data set and therefore be something interesting to look at to identify the hubs in your connectivity because they may contain information that is relevant to class divisions, that sort of thing. So what we can do is we have this parameterized feature space, high-dimensional. We can construct a minimal spanning tree for it. We can break the minimal spanning tree up at various edge lengths. We can identify those things which are outliers in terms of they have a very low connectivity and also they have a high persistence, and then we consider those to be topological outliers. Or topologically identify outliers and then see how they compare to a density outlier. So that's the sort of thing I've been playing around with a bit. All very nice and theoretical. So where does that go? So here's an example of a deterministic outlier. And what I'm going to be showing for the rest are outliers that have been identified by both the sort of normal density investigation, but also are validated by the topological approach. So this is a mode switching RLI that Andrew Drake found a couple of years ago in Catalina data. This stands out in terms of features which you believe are encoding deterministic information, where there's, it's period or something like that. So what we have here is the thing actually goes along here, and then suddenly something happened internally to the star which increased the amplitude of the variability and also slightly changed the period. And when we phase it up, you can also see there's a waveform change there. And if you talk to our RLI experts, they will theorize that maybe there's some sort of chronospheric activity and gradients going on inside which change something, and then there was sort of flip on the mode to another sub-mode, this sort of thing, and then run computer simulations on it. But it's a nice example of an outlier in terms of underlying deterministic processes. Now, I'm interested in AGN, and they are much more something that's stochastic. So what do we mean by that? We mean that something that's really describable by a linear differential equation driven by a white noise process. So Black-Scholes equation for the stock market. Stock market is an nice example of a stochastic process. However, it's not the same type of stochastic process as what we see in a lot of astronomical phenomena. We've done some analysis using the sort of things they do, and we find out that the stock market is much more volatile than astronomical processes are. But what sort of things could be this? Well, this could be periodic or episodic behavior with an incoherent attitudinal phase variation, stellar chromospheres, or accretion disks. So here's an example of a sort of node cataclysm variable. It's stochastic. So what can you say about these? Well, let's look at quasars. So the first quasar, one of the first quasars in 3C48, it was noted in the paper that its most striking feature was that the optical radiation varied. So we've always known that these are variable sources. The physical origin of the photometric variability in quasars is not clear. There are a number of mechanisms, but we don't really understand what is causing it. Sort of believe it's something to do with the accretion disk, but we're not really certain. And there are people who've said that there may be other things going on there. Many of the studies that have been done on quasar variability before the Strike 82 study were done on either very small sample sizes, which have been sampled very heavily, or on very large samples which only had sort of 3 or 4 data points. So the variability you ended up looking at was a sort of ensemble thing, very much information. Currently, the best statistical description for the variability that you see as a statistical description, which means that you can't necessarily infer any information on it, is a dense random walk, a thing called a continuous or first order regressive model, which is characterized by two parameters, some sort of variability and a characteristic timescale. Now, in the Catalina data set, we have light curves for 335,000 spectroscopically confirmed photons. So those are 10-year light curves with 250 typically data points for 335,000 quasars. So this is the ideal data set to start looking in a systematic way to try and understand what quasar variability is really about. It's an order of magnitude bigger than what's gone on before. Now, in terms of features, we were looking at various features, and one of the features that we found which was particularly useful is a thing called Slepian wavelet variance. You heard John talk about wavelets yesterday. Slepian wavelets are a very nice type of wavelet that works very well with regular and gappy time series. And wavelet variance is a way of analyzing wavelet coefficients. So we can say that you can decompose your time series, as Jean-Luc was saying yesterday, you can use a dictionary. In this case, we're using a dictionary of wavelet filters, Slepian wavelet filters. So we can decompose our time series in terms of these, and then we're interested in what the values of the coefficients in that decomposition at a particular time lag or particular time scale, because wavelets allow us to do a localized time and frequency analysis. And what it turns out is that the wavelet variance, the variance that we see from those coefficients, allows us to say what the contribution to the total variance of the time series is at a particular time scale. So that means that for a given time series, we can identify within a dyadic range, because these are wavelets, but we can identify the particular time scale at which some processes are contributing the most variation to the total variance of the time series that we see. And if we plot variation against time, that allows us to identify characteristic scales, because you would expect those to be identified with peaks or with changes of behavior in that. So it's a very useful diagnostic tool for trying to understand, really get some level of information out of what's coming. Can we identify real time scales of physical processes in this which are contributing to the sort of stochasticity that we're seeing in this? So what happens when you look at quasars? Well, what it turns out is that, so this is the variation, this is the time scale. Forget the units, it's a log 2 scale. But quasars have this behavior and stars have this behavior. So this means that we can actually use this as a way of identifying quasars from non-quasars. What's even more interesting, however, is that when we generate simulated quasar light curves according to the best current statistical description we have, which is this CAR1 process, we find that at particular timescales, at short timescales, the CAR1 model is very good. It agrees with what we see in the real data. But past a particular point, we see a deviation in quasar light curves that we do not see in the CAR1 model. Now, there have been a number of papers recently looking at Kepler AGN and more detailed, more heavily sampled quasar light curves, which are basically agreeing that the CAR1 model is a good model across the whole family, if you want to describe it, but actually it's not a perfect model because it breaks down at particular scales, and that's what we're seeing. It's not only a limitation, it's not only a feature, this breakdown of our particular data set. Maybe there's something peculiar in our data set. When you look at the stripe 82 quasars as well, you do see this deviation as well. Not so clearly defined, but that's because we have better time sampling, or we have a richer time sampling in the Catalina data than we do in the stripe 82 data.
So what is the unit for timing this one?
this is log 2 of days. So it's base 2. So this is about this is the 56 days.
If you look from topology perspective, this car model doesn't really deviate from topology of the stars.
No, but we're not. So we haven't. Where we look at this from a topological perspective is then we look at the encoding of this in the parameter space, and then we're looking for outliers in terms of those objects. So what we're interested in doing is this allows us to characterize our population of quasars in terms of wavelet features, and then we can use the wavelet features in the parameter space and identify those outliers in terms of the wavelet features from both the topological or from the density perspective. And this is what I'm moving on to now. So when we do that, so this is where we're getting onto the sort of outliers we're finding in the quasar populations now. From doing this wavelet analysis, find those objects which don't look like the general types of behavior that we see in wavelets. Because the idea is that, as I say, population behaviors tell you about the broad class of objects, but the outliers are the interesting ones because they're the ones that may give you some insight into the weird physics that's going on and give you some sort of more information. So here we have objects which is nice and flat, and then started increasing and then has leveled off again, which is not shown. And if we were lucky in that there was a Sloan spectrum there, and there was a Voss spectrum halfway through, and then we got a spectrum at the top end. And what you can see is that this is a very strong VAL quasar, broad absorption line quasar, and you can see that actually the changes in the photometric variability are consistent with changes in the broad absorption line drops. This is an iron low Val quasar, time very fast, and people who understand these things tell us that this is indicative of changes in photoionization equilibrium. So this was an outlier in the parameter space. We look at it spectroscopically, it's also changing, and then we can get some insight into the physics of photoionization in the VAL clouds from the source. Here we have another one. This is so we have linear data here, which tells us it's flat. There's the Sloan spectrum, and then it started increasing, and it's increased by 2 orders of magnitude, and there's some PTO data at the end there. That's when we look at our spectrum. And here you can again see the spectroscopic variability here. This is a changing look quasar. This is a double peak emitter, which is going to a single peak emitter, because there's something going on with the clouds and stuff like that. Possibly the most interesting one we found was PG1302. So this stuck out as a very strong outlier in our parameter space, and when we looked at it, we saw that it seemed to be periodic. Periodic quasars don't exist, that's what we've been told. We did some more analyses, and the periodicity seemed to be real. We got some more data. We looked in the literature at the historic data, so we get about 4.5 cycles here. The period of this is 1880 days in the observer frame, it's 1400 days in the rest frame, which is about 5 years. HST imaging shows it to be a disturbed morphology. It has some very, very close pairs, very close nuclei within a couple of kiloparsecs. The spectrum is very boring, however. There are radio and optical structural features which are indicative of some sort of disturbed morphology in the past. And the idea here is that actually what we're seeing a binary system. We're seeing a supermassive black hole binary system. This is what we detected. Now, physics of supermassive black hole binary mergers, they hang around for a long time. When they are less than 0.01 of a parsec apart, gravitational wave radiation takes over, and you start seeing interesting things before they turn out to possibly recoil. Now, sub-parsec systems are not resolvable from the Earth, even with VLBI, but when we do the separation of this object, it's at 0.01 parsecs. So this potentially is a new way of finding these very close sub-parsec pairs. There have been a number of spectroscopic searches in the literature in the last 10 years, the idea being that if you have a binary pair, maybe you will see some sort of Doppler effect on the emission lines with time, but they haven't really found anything particularly yet, and when you do the math, those are limited to 0.1 parsec separation systems. They can't get these very close pairs. Whereas what we believe is that with this photometric variation, if we could find these, then we are susceptible to the ones which are much closer. The best example of a binary candidate to date was OJ287. This is very bright. It has 100 years worth of data. And the idea here is that it peaks every 12.2 years, because what you have is you have a 100 million black hole mass, 100 million solar mass secondary, which goes through the accretion disk of the primary every 12 years, and that creates flares. So this is a very different morphology to what we're seeing with PG1302. This is what the Catalina data looks like for OG287. It's not a full cycle, but you can see it's a very variable object because it's very active laser.
So it goes through the accretion disk twice?
Yeah, it goes through once, and then about a year later it goes through again, which gives you a pair of flares which are separated by a year every 12.2 years, is the idea of OJ287. So, having found PG1302, we decided that we would try and put together some sort of research criteria to see if we could find some more of these than 335,000 objects. So, various ways of autocorrelation and shape coverage, and we found the number, and then we used that as a trade concept in SVM to try and better find that discriminating hyperplane. Now, with the data set that we have in hand, and with what people think about supermassive black hole binaries, we estimated that there should be about 450 binaries predicted. With a reduced set of 250,000 quasars, for which we actually have decent data, good sampling, we found 111 candidates. When we simulate the data again with CAR1 models, just to make sure that we're not just detecting noise, we get no candidates. So what we're detecting is not just an artifact of a CAR1 model. These are some of the binary candidates we put out a couple months back. I mean, the red lines are pure sinusoidal, are only there to API. We don't suggest that's fitting the model in any way. But you can see that these are all broadly, or look broadly, periodic over at least 10 years, slightly longer when we have linear data as well, that sort of thing. So it's an interesting data set to continue monitoring for that. Now, the Karma 1 model, the Karma 1 description, is just a first-order autoregressive model, and it's the simplest stochastic model you can use to describe something. A more general form of the stochastic model is what's called a Karma model, which is a continuous autoregressive moving average model, which can have higher terms and various parameters involved. But the important thing is that the power spectrum density for this looks like this. And you will see that there's a term underneath here that if the frequency that you're looking at is very equivalent, is very close to one of these parameters, you're going to get a spike in the power spectrum, which will give you quasi-periodicity in your light curve. So, can we be sure that what we're seeing in those 111 is actually physically real, and not just a consequence of it actually being a more involved stochastic process, stochastic model that we're seeing? So what we did is we fit each of the 111, determined what the best fit Karma model for those is, generated mock light curves for each of those based on those, and see if we found the same periods, and we did except for 5 cases, but the bandwidth for those 5 cases is so wide that basically any period is fitting through. So we can be fairly certain that what we're seeing in the periodicity, that periodic signal is physically real in some sense, and it's not just an artifact of the stochastic process that's generated. So what is it? What is causing this? Well, we don't know. Is the the bottom line. There are a number of possible physical mechanisms that could be producing this periodicity we're seeing in these outliers. It could be superposition of thermal emission from the accretion disk plus a non-thermal component from a precession jet caused by a binary, because the timescale of precession requires a binary. Timescale of precession for a single jet doesn't work. There could be a warped accretion disk, but most warped accretion disks are associated with binaries. There could be periodic accretion rates from the supermassive black hole binary, which leads to an overdense hump, which is what we're seeing, so we're seeing more flow. Hydrodynamic simulations suggest that the strongest periodicity is associated with a cavity in the certain binary, and that the true binary period is actually maybe even a factor of 10 smaller than what you observe. So instead of it being 0.01 parsecs, these things are even much closer than that. There was a Nature paper out 2 weeks ago by some of our colleagues who are suggesting that this may actually be relativistic boosting. You get Doppler boosting from mini-disk around the secondary, which is orbiting around the system barycenter, which would give you the sorts of things that you would see. And there are predictions of that, which are dependent on the spectral slope of the quasar spectrum, the SUV. And when they've looked at UV data that's available for PT1302, that is consistent with the types of variations you would expect to see. So it may be that the PT1302, at least relativistic boosting, is the mechanism. It may also be that what we're seeing here is a scaled version of the sort of quasi-periodic oscillations you see in stellar black hole bubbles. Whatever physical explanation we can come up with, which seems realistic, however, it falls back on the physical fact that we require a binary system. So it's quite possible that within that 111 sample, we are actually seeing a number of different mechanisms causing those periodicities, but fundamentally we are still seeing these supermassive black hole binary systems, which we expect from galaxy mergers. You know, every galaxy has a supermassive black hole in the middle, galaxies merge, the black holes have to do something, so we should be able to take something. Other reports in the literature, well, they don't look like these objects when you look in the Catalina. So I don't know what the other binary candidates people have seen in the literature are. Who knows? We can test these. Some of these mechanisms make predictions about the sort of things. So X-ray imaging, spectroscopic monitoring we're trying to do, color monitoring, obviously, color information reverberation. So there's a lot of things we can do to try and confirm these and look for predictions. More interestingly is that some of these objects are close enough for a particular end phase of the merging process that they should be giving out gravitational waves. And Lawson-Hyman predicted that it should follow this T to the 8/3 power law, which is convincing that maybe that's what we're seeing. We lose up at a large scale because of accretion physics. But what this means is that there is certain binary gas present and it's being perturbed by black holes if this is correct. And in terms of whether we could actually detect the gravitational waves from this with pulsar timing arrays, well, this is where the Parkes pulsar timing array is, and it's very sensitive. Not that far off, so maybe with the next generation with SKA or something like that. Conceivably, and one of these happens to go off within the timescale we're looking at, you may actually be able to see this as a direct signal as opposed to just a stochastic background signal. So it's possible. So, time domain is the new exciting frontier of astronomy research. I will happily argue current surveys such as Catalina, PTSE here already offer great opportunities for scientists to discover if you need to get your teeth in, get your hands dirty, get the experience you need to do with data sets which are very similar in scope and scale to what you will have with LSST in terms of doing analysis. Future surveys such as DTF and LST will obviously radically transform our understanding of the universe. Potentially the most exciting sources are the outliers. And we need smart ways of characterizing and identifying them and then figuring out what they may actually be telling us about some of the interesting physics logic and stuff that's going on. So, thanks.